Hi, everyone, and thank you for picking late flights. The plan for the talk is I'll introduce singular foliations and try to motivate why this is the notion that we are using for singular foliations is the right one, and then try to give some structure theorems of them near leaves. This is based on a collaboration with Camille Laurent-Gengoux. So, okay, let's get started. What is a singular foliation? And in the beginning, if we take a starting point, something we learned in differential geometry 1, we kind of have two choices. We could say that for a regular foliation, we already have two characterizations. We can say that it's a decomposition of a manifold into leaves, which are submanifolds. Which locally looks like the trivial decomposition. So, which locally looks like we're foliating, let's say, Rn into Rk pieces, which then are parameterized by parameters in Rn minus k. And the Frobenius theorem tells us that instead of having this slightly bulky definition, we could also simply say that we take a subvector bundle of the tangent bundle, and we require it to be involutive, so that the Lie bracket of sections of this subbundle is again inside the subbundle. And on the somehow for generalization to the singular case, the left-hand side looks highly unappealing because, okay, we can say it will be a decomposition into submanifolds. We don't require them to be of same dimension, but what should the models be to which we compare singular foliations? I mean, we can imagine if we have a singular point of some decomposition into submanifolds, around it things could look like this. They could look like this. They could look like spirals, and so on. So the starting point of the problems is, for a singular foliation, we wouldn't know how to define it by how it looks in a local neighborhood. So we would go to the right-hand side and then maybe eventually prove some theorem about local structures. So first, attempted definition. Of singular foliations. We take D subset Tm, a family of subvector spaces, without requiring that it is a subvector bundle, so they can jump in dimension. And we can say for sections of the tangent bundle, which have values in this subset, we want the bracket to also have values in this subset. So we can, again, just ask gamma D to lie in gamma of D. And this definition has tons of problems. So problems. The first problem is we would like this to be equivalent to something geometric. So we could say, okay, from such a distributions, I try to build somehow the maximal submanifolds going through those subspaces of the tangent spaces, and that gives me something geometric. And then I look at the tangent spaces of those objects and would like to recover D. And this will not be the case. So if not every element of D can be realized as a tangent vector sorry. How do I want to say that? Not every element of D. Not every element of D can be realized as a value of a vector field in D. So that's somehow a slightly more precise way of phrasing it. I can define, for example, a decomposition of a manifold into submanifolds, which will look like this. And here, the elements indeed that go vertically cannot be smoothly extended. So if I take basically the sections of D, I will never see those vectors which go vertically. If I take this subspace, generate D from it, and then from this D generate again a manifold, a foliation, it will look like this. So this line will be broken up into points. The other problem is leaves could just not be submanifolds. So for instance, I could build something where I take in the tangent space of R2 all horizontal directions, and then right to the right side of the origin, I add all vertical directions. And this thing behaves very weirdly, because somehow, with every reasonable notion of leaves, if you look at this place, you would be only allowed to move horizontally. But if you go around, go a little bit up and go back, you come back to the same place. So somehow near this place where you start adding the vertical directions, it behaves really horribly and you cannot really properly work with it. So those are somehow the two primary problems. So leaves are not submanifolds, and we could lose some information when going from geometric to infinitesimal and back. And then there is a third problem, which is more a question of taste, and that's that sometimes we don't only want to remember the subspaces, sometimes we want to remember how we approach the singularities. So sometimes it is nice to know more about singularities. So I'll make this a little bit more precise in a minute. Okay, so the A definition that resolves those problems is the following. Singular foliation is a subspace F of the compactly supported vector fields on M, such that first, if a vector field is tangent to a foliation, so if it is in this set F, I want any multiple of it to be tangent to the foliation in the sense of multiples in the sense of smooth functions. So C infinity M times F is supposed to be contained in F. It's a C infinity M module. Second, exactly the involutivity that we had already in the regular case. And then there is a third condition, which is F is locally finitely generated. So since it is a C infinity M module, I can localize to little coordinate patches. And there, I want to have a finite set of generators. So F is locally finitely generated. This is a condition because smooth functions are an annoying algebra. So if you work in the analytic category, you don't have to think about that. This is more to avoid weird things with flat functions. So don't think about this too much. Okay. So if it is, this is a reasonable notion to be on the right-hand side of the diagram, then hopefully there is something to be put on the left-hand side. So there should be a decomposition into leaves, which are submanifolds induced by it. That is a theorem which has been proven in a chaotic back and forth, and it's called Hermann or Stefan Sussman theorem, or even, I think, a few other names. There is a nice historical review on it by Sylvain Lavaux. Sorry? It's still being proved as we speak by someone. Sorry? Yes, so this F a priori has nothing to do with submanifolds. It's a submodule of the vector fields. That for me would be fine. A torus with irrational slope is fine because it can be localized, so the connected components of the leaves look good. So, and as a module, that's absolutely fine. In the tangent spaces, you don't see that the slope is irrational. So, theorem. Hermann, Stefan, Sussman, Otto, and others. If you put together all points on the manifold that you can reach from one single point by flows in the foliation, you get submanifolds. So M is a decomposition into L alphas, submanifolds. And L alpha is wherever flows of F get you from a fixed point. So phi x1, phi x2, and so on, phi xk, t1, t2, tk, of some fixed point for arbitrary collections x1 to xk in the foliation and arbitrary times t1 to tk in R. Okay, so this, from here, without kind of going further into the geometry, we already see in which sense this attacks this thing that we want to know more than the decomposition into leaves. Because, for example, the if we look at the vector field x dx in the vector fields on R, and so I'm using those brackets to denote C infinity span of it. This will be a different thing than x squared dx in the same space. And so in some sense, this really, this F really remembers how we approach singularities. There is now, before I go to examples, a theorem which basically takes the role of the Frobenius theorem. This theorem has been reproven even more often than the Hermann theorem. The original versions of it, as far as I know, are from Servo and Dasor theorem. Dasor. And others. Near a point, F is always isomorphic to, and now I write down a foliation in local coordinates. The foliation generated by dx1 to dxk and f1 of y dy1, dyi1, fky dyk. So the, sorry? Okay. Okay, so this, I think, this theorem is quite central. I should say that this theorem have been proven quite a few times, but then a little bit forgotten, and actually reproven relatively recently by Skandalis and Androulidakis, who chose this definition of singular foliation, or who proposed this definition to do to work with C-star algebras of singular foliation and define holonomy groupoids. So I will add an attribution that this is Androulidakis Skandalis. So this theorem basically says that when we look at the singular foliation locally, we can completely split from each other some regular direction, and then somehow, some way, how it behaves in those directions. And this theorem already tells us that somehow how it behaves transversely in those additional directions does not change from point to point on a leaf. So it is a local normal form result. Because I don't like coordinates, I would like to rewrite it to just introduce the notation for later. I would write that f p is equivalent to x of x px times py, and t is in IPy x of y. So I will now explain all the letters. The idea is I want to, if I talk locally, I'll just say fix the point, and the idea is there is an open neighborhood around this point such that it holds true. And so near a point, f is equivalent to the foliation, which just contains all vector fields. It's a regular foliation. This is the dx1 to dxk directions. And some foliation tau called transverse foliation, because it's exactly the non-leaf directions, with a foliation which vanishes at the point py. And so this is the ideal of functions vanishing in py. F and c infinity y vanishing at f1 of py is 0. Yes, so I take an arbitrary vector field and multiply it by a function vanishing in 0, and then I take finite sums of those. I could also somehow define it directly. A foliation made up of vector fields vanishing in py. So it's yes. So those are functions, but I could also just call this thing vector fields such that x in py is 0. Okay, maybe it's time for a few examples beyond one-dimensional. And most examples are elementary, and one of them is actually, to some extent, my motivation to work with singular foliations. And I'll start with the most abstract one and then make it more concrete. Examples. Let's take an NQ manifold. So it's a positively graded manifold, or non-negatively graded, with vector field squaring to 0. Those are certain DG manifolds. Or, if you prefer the term, L-infinity algebroids. So there are many ways to think about it. But if you think about them as you have a manifold, and then you have an algebra of functions, which looks like the symmetric algebra of some graded vector bundle, then the Q gives you a differential, among other things, on the vector bundle. So if C of M is isomorphic to gamma of S of some graded vector space dual, then Q induces a differential, and it goes from E minus 3 and so on. So you have a series of a vector bundle with a series of maps, which always concatenate to 0. And then you have a last one, which is called anchor, which goes to Tm. And in fact, you have more things. For example, you have something which is almost a Lie bracket here. It will be a Lie bracket up to something coming from here. So you do have a skew-symmetric bilinear map here, and the Jacobiator lies in D of something. So if you are in this setting, which I have been told does play quite a nice role in physics, then the image of through the anchor map is a singular foliation. So rho star, or yeah, rho of gamma E minus 1 in gamma Tm, so in Xm, is a singular foliation. And I think I'm being a little bit inconsistent here. I chose the vector fields to be compactly supported, so I should take compactly supported sections here, and probably compactly supported on one of the previous blackboards. So this is an interesting example, but maybe too general to be called an example. The most classical case is when your graded manifold is induced by a Lie algebroid. So sub-example. E over M with an anchor to Tm, Lie algebroid, i.e. on the sections of E you have an honest Lie bracket which behaves well with the anchor and is and satisfies the Leibniz rule with respect to multiplication with functions. Then it's the image for the anchor is a singular foliation. This example includes all regular foliations, which can be interpreted as subvector bundles of Tm with the bracket of sections of them being, again, a sections of them. So the bracket of vector fields just defines a bracket on sections of the regular foliation. And that is exactly the way how you can encode them. So sub-example. E is equal to D regular foliation. Other instances of Lie algebroids, which are already interesting, is you take a Lie algebra action on the manifold and to take the action Lie algebroid. So another sub-example is E is equal to M times G, and you have an action on M, which gives you through the fundamental fields such a map. And then you recover as leaves the orbits of the action, or if you have a non-connected group, the connected components of the leaves. So connected components of orbits. Yes? So you have just found the trivial foliation, which just decomposes M as a disjoint union of all of its points. Q square should be 0. So the quote, yeah, that's it. And Q manifold degree plus 1. Basically, in this picture, the important property to show is, okay, in the smooth category, locally finite generation. This is a vector bundle. It has locally finitely many generators. Their images will be a generator of the image. C infinity module follows from the fact that the anchor is a C infinity linear map. And the fact that you're involutive follows from the fact that the Jacobiator here is something coming from E minus 2. And because Q squares to 0, it will be 0 in Tm. When I talk about NQ manifolds, I assume that they are degree-wise finite dimensional. So I impose that as one of the properties in the definition. If you start talking about infinite dimensional manifolds or infinite dimensional vector bundles over finite dimensional manifolds, the situation gets more complicated. So then, yeah, I think then basically all the theory which requires leaves to exist somehow breaks down, and one runs into problems. Oh, yeah. So I want to give one other example, and then an exercise for the people who know all those definitions. So another example. I take the ideals of functions vanishing in 0 in R2. I take its square and multiply it to the space of all vector fields on R2. So this is all vector fields that vanish quadratically in the origin of R2. They are generated by x squared dx, xy dx, y squared dx, x squared dy, xy dy, y squared dy. So we are on R2. The minimal number of generators for the foliation is 6. Conjecture, this cannot be generated as by a Lie algebroid. So this is F. Conjecture. There exists no Lie algebroid. A such that rho of gamma A is equal to F. This is, for me, at least slightly shocking that this is unknown. But yeah, so there have been invariants computed which should somehow calculate whether something comes from a Lie algebroid, but unfortunately they only check in minimal dimension. So if I'm not mistaken, there is a theorem that there is no 6-dimensional Lie algebroid generating this foliation, but maybe there is a 7-dimensional one. Yeah, homework. Sorry, did I write one twice? X squared dx, xy dx. Yeah. So I might have written one twice, but that would be an error. So just all quadratic polynomials times all d somethings that I can find. Okay, I think I'll have to erase quite a bit. So we have time for questions, comments, corrections, lists of further names of people who have proven the theorems that I have written. Mm-hmm. Yes. Yeah, it's, I mean, I think I have seen, I'm not sure if it follows directly because this gives you somehow this local statement, but then you still need to find out that things don't go wrong globally. And I think there is some hard work in there. So the Hermann theorem, I think, is a priori more general than what I wrote down. But even its restricted case to singular foliation is a little bit more than the local normal form. So and since we have seen that seeing when a foliation comes from a Lie algebroid, for example, is difficult, one can also assume that saying, for example, when two foliations are equivalent could a priori be difficult. And thank you. And that's why what we're going to do next is try to construct invariants of singular foliation. So ways to extract some information without having to work with the module anymore. And the first invariants we are going to define are the isotropy Lie algebras, and then we are going to see that actually we can do it along a leaf and get something which is called isotropy Lie algebroids. But looking at the time, we probably will talk about them more or less at the same time. So let F be a foliation. X a point in the manifold, and L a locally closed leaf. So here I'm requiring something which avoids dense R's wrapping around the torus. We have already got to know Ix, so the functions that vanish at X. And we will similarly define IL, which is the functions that restrict to 0 FL is 0 to the leaf. So definition. Gx is equal to F modulo IXF is called isotropy Lie algebra. Sorry, yes, thank you. F intersected with IX all vector fields. Yes. So it is a small computation that this is indeed a Lie algebra. The finite generation of F implies that it is finite dimensional. After one knows the theorem which splits a foliation into leaf and transversal directions, one sees directly that this is measuring exactly the transversals. And the next thing we are going to do is we are going to define the holonomy Lie algebroid, which is now something living along L. So we define AL as the Lie algebroid satisfying that gamma AL is isomorphic to F modulo ILF. So here there are a few theorems used. First thing one needs to observe, this will be a Lie algebra. Second thing one needs to observe, due to the local normal forms theorem, it will be a projective C infinity L module. And then one uses Serre's one theorem to say that there is a vector bundle such that this thing is the sections of the vector bundle. And then the Lie bracket here induces a bracket here, and one also has to show that that is well compatible with the anchor. So there is some work coming into here, but we now have can build a Lie algebroid. And if we want to understand a Lie algebroid, we have to understand two things. We have to understand basically the image through its anchor, so what happens on the manifold, and we have to understand the isotropies, what somehow happens in the directions invisible from the manifold. So AL to TL, it's a Lie algebroid over L. We have, this is a C infinity L module, is surjective. So we have a transitive Lie algebroid. And the kernel will be exactly all the isotropies put one next to each other. Okay. Yes. So it exists, and it is, by this property, is uniquely determined up to some canonical isomorphism. So this Lie algebroid is relatively big. So for example, we had this foliation of vector fields vanishing quadratically. It was 6-dimensional. Often one needs something smaller to work with. And the smaller thing that we will use is the linear part of the isotropy and the Lie algebroid. This is not directly a notion which we can define for a Lie algebroid. This is something which comes from the fact that the Lie algebroid comes from a foliation. In the foliation, near a point, we can say what does it mean to be quadratic. And so we can here just say, we don't just divide out IXF, we will also divide out IX square any vector field. So any vector field which is quadratic will be annihilated. And this will give us, again, a Lie algebra, which will be smaller, which will be called linear holonomy. I will not write it into here because it will be quite unreadable. So there is GX lin, which is F IXX divided by IXF plus IX square of all vector fields. And I can build a Lie algebroid AL lin, whose sections are F modulo ILF plus IL square X. And again, with the local normal form result, we can show that there is a unique Lie algebroid satisfying those properties. And this thing is a quotient of the previous one. So in total, we get AL going to AL lin, going to TL, so a sequence of algebroids. Yes. Thank you. So this letter invariant is computable. We basically only need to know the first jets of the foliation in some sense. And since this thing has been defined using the foliation, so we have something like a map here, which I'm writing dotted because it's not a Lie algebroid map. It's actually a map into the sections. It's just for kind of a reminder. So we had, now I have 15 minutes for the actual topic of the talk. That's much more than I need. We started with this local normal form theorem for foliations, which said that locally we can split apart the leaf directions and the singular directions. And now the natural question would be, when is a leaf trivial? So when do we have a leaf? And the foliation near the leaf looks basically like all vector fields in a few directions and some singular foliations in the others. This question can be translated as follows. When does foliation admit? Yes. Admit flat Ehresmann connection, which is something I will define now. Action, i.e. action from vector fields on the leaf back to the foliation. And so along a leaf we can restrict, and we would like a map back, which is a Lie algebra homomorphism. For this to kind of, to work with this, it is good to localize near some open neighborhood around the leaf. So, so we would like this to be true on some open neighborhood, which contains the leaf. And we would like this to be not just any vector fields, but we would like this to be projectable ones. So ones which, at least in the leaf directions, do the same thing. And when I say projectable, so I will define it now, because actually I don't just want L to be a subset of U, I want a tubular neighborhood U of L. So I want U pi L inclusion to be some neighborhood which retracts to L, and then I can talk about projectable vector fields on U, and I can demand, I have the restriction homomorphism, and I can ask, is there a section in the sense of Lie algebras? So, and this is some sort of measure of how trivial the foliation, the topology of the foliation is near the leaf. So can you completely split apart the leaf directions and the singular directions? If such a thing exists, then thank you. So flat Ehresmann admit a flat Ehresmann. I will add F connection because it's not just any connection, but one with values in the foliation. Flat Ehresmann F connection plus simply connected leaves implies that F is isomorphic in a certain sense to X of L times some foliation vanishing at a point. So with simply connected leaves, this notion of flat Ehresmann F connections is exactly what tells us that this local splitting can be done along the whole leaf. Careful. When I write such things, currently the theorems are proven at the level of jets. So getting things to actually converge is really hard because one needs to do Lie algebra cohomology with normed vanishing in infinite dimensions. So this is at the formal level. I will not make formal in this talk, but one should think about it as infinite jet. Yes, we have the formal result. So the answer to the do leaves admit flat Ehresmann F connections is basically usually they don't. But what we found with Camille is a slightly weaker notion where we can still describe a foliation in such a way, even if it is not trivial near the leaf. So I'll write down the theorem, then explain the words, and then we'll be done. So, theorem. Let L be a locally closed leaf in a locally real analytic singular foliation F. F if first pi1 of L is 0, and second AL lin is semi-simple, then F near L formally is isomorphic to the sections of AL lin semi-direct with a certain foliation which vanishes at a point. Okay, so the result we have proven is actually a little bit stronger, because we just instead of this can work with the semi-simple part of the linear holonomy and require a weaker condition than this, but this is one of the cases where that appears. And in those cases, it is not a product, but it is at least a semi-direct product. And in addition, a few things that I did not mention today, one can manage that, one can find a linear structure on the tubular neighborhood of L such that actually the action is linear in a formal sense. This description in particular implies that AL lin acts on a tubular neighborhood of the leaf in F. And it then acts by vector fields which are linear up to something flat. So because we have the statement only on infinite jets, we then know that the Taylor expansion of the vector fields will be linear, basically. But there could be some flat nonsense going on. So so this statement is somehow a particular case where we can get a section from TL to AL lin, and then we can assure this theorem. If the foliation is transversally quadratic, then this condition is trivial, because this will just be TL and the isotropies will be semi-simple. So in particular, if we have a foliation which is transversally quadratic, it looks along a simply connected leaf like the product of vector fields along the leaf times something vanishing in 0. So corollary F transversely quadratic implies F looks more or less like XL times tau, where this vanishes at the origin. F comma L, it's like in a neighborhood of L. Origin. Okay. Yes? Here it is meant that the isotropy algebras are semi-simple. Those algebroids are always transitive. So pick one point, pick its isotropy algebra, and we ask for this to be semi-simple. Actually, there a little bit of work is hidden, because for the argument that we use, we need h1 to be 0 of the Lie algebroid with values in any flat module. And there, this semi-simplicity is not enough. We actually, in addition, need that pi1 of the leaf is 0. So there's a spectral sequence intertwining the Lie algebra cohomology and the cohomology of the leaf, and then. So if pi1 is not 0, we could. So getting up, I think, is possible, but getting back down is problematic. So we are working on some version of the theorem for the not simply connected, but it cannot be that simple. We can build examples where it is where L is not simply connected, where bad things happen. It's like if you take a cylinder that goes into its insides back and forth, and in this center you have a circle, then those things, like this cannot be covered by a theorem of this sort. Sorry? Exactly. So somehow this these sections and linearizations can only exist if the holonomy is trivial and if the higher holonomies that you can construct using NQ manifolds are also trivial, because such a flat Ehresmann connection basically kills them all. Sorry? Flat Ehresmann connection is very restrictive because you need the linear holonomy basically you need a section, you will automatically have a section into the linear holonomy. That means that the tubular neighborhood, for example, for a simply connected leaf is trivial, like on the topological part. But it is much easier to have something from the semi-simple holonomy into the linear holonomy, and that is all we need. So there is somehow this wider framework where results still are possible.